All right, everyone, we are back and we're going to go through our question 3, so our Fourier related questions. So let's look at the frequency spectrums below, match the Fourier series written for the spectrum, what's the period that you select? So once we select one, what's the period, lowest frequency, maximum frequency, dominant frequency? So we have this Fourier series here. So we're given in rads, hertz, and hertz. So we should look at essentially, there's a couple ways you can approach this problem. One, we know that this first term is going to be A naught over 2. But if we're looking at the frequency spectrum, we know that C sub n is equal to square root of A sub n squared plus B sub n squared. We know that B sub 0 is always equal to 0. So therefore, whatever our, the magnitude of this has to be, this is going to be A naught over 2. So A naught over 2. So basically we know that this has to be A naught is equal to minus 20. And therefore C naught is going to be equal to, 20. Because 20 squared, minus 20 squared is going to be 20. So that's what we know. So this one's automatically dead. This one's automatically dead. It's got to be this one. Does that make sense in this problem, or does it match whatsoever? Let's take a peek. So let's go ahead and let's see this problem. We are given that it's, point. So this is again this is omega. So I think these intervals are 2, 4, 6, 8. Yep. So you can see here, this is 0.6, and we see 15, which is good. Then we have 1.2, which is right here, which is root 5, which does make sense, right? Where's our 1.2? So we have here our square root of 5. But this square root of 5, should not be correct, because if we don't see this frequency again, this needs to be 5. So we can see here our 1.8, that works because it's 10. We can see here as well for 2, this one's not existent, so it's 0, fantastic. 3, we see it's 20, good. This one's not existent, and then 4 point, actually, we should see each of these intervals, and 4 point, what is it? Actually, 2 doesn't even exist. This one, let's actually look at this just quickly here. Sorry, I'm just zooming in. Because right here, our delta fundamental has to be 2, 4, 6.6. So then this 1.2, then this 1.8, 1.8, 2, 2, 2.4 makes sense. 6, this, 6, and then 3.8, 6. So we should have, let's see here. We should have 3.6, and then 3.6 plus 6 should be 4.2. So none of these actually work. So none of these will work, so we don't even have to answer that question. But if we did have to choose for this one, this would be our maximum frequency. This would be our dominant frequency. Our lowest frequency would be the fundamental, which is 0.6. And then our period would just be, so omega equals, or our, basically 2 pi f. Our lowest fundamental frequency is 0.6 equals 2 pi f. We would solve for that. So our delta f is equal to 0.6 hertz divided by 2 pi. And then our period t is equal to 1 over, or basically delta f is equal to 1 over our period. There we go. So let's go ahead and let's go to the next problem. Recently watched my octopus teacher, found there's these frequencies. So these are basically in omega. So we need to basically take each of these and do, so I'm going to actually make a list of frequencies. So I'm going to go over here. Where are we at? Here we go. Let's go over here. And I'm going to say freq list, or just say, I'm going to say f list. And it's going to be 3 times pi, 3 pi, 8 pi, 15 pi, and 10 pi. And then we're going to divide all this by 2 pi. So these are our frequencies, and let's look at them numerically. So here are our frequencies that we have to hit. If there are no constraints, what will be your choice of sampling frequency, period, number of samples to allow you to accurately sample the octopus? So if these are my samples, so this is FS JPS. So if I can choose, if I was unconstrained, I need to be at least twice basically my highest frequency. So let's just say I want to be, heck, I'll do 50. 50 will ensure that. My delta F JPS, I need to be able to hit each of these values. And if I just pick 0.5, I'm going to be able to hit that. And now I can solve for, so because my period, FS, so my delta T JPS is going to be equal to 1 divided by FS JPS. And then, so we're going to solve my period, but we have not solved delta F. So basically my period, delta F, is equal to 1 over my period, which is big N times delta T JPS. So if we have 100 essentially samples, then we're going to be able to hit each of those frequencies at a delta F. So, and when we know that if our FS is this, our F Nyquist is a half of that. So we will be able to hit essentially those values. You can confirm this in a number of different ways to solve for your big N. We can also say solve. So our F Nyquist is going to be 25, and that's going to be equal to big N divided by 2 times delta F JPS. And you can see we get the same value there. So if you want to think about Nyquist frequency, or if you want to kind of work it this way, there's multiple ways to solve that problem. So this would allow me to accurately sample my system. But now for each of these graphs, we have to determine delta F, delta T, Nyquist, F sub S, and N. And then answer the question, did any of our undergrads basically sample this correctly? So I'm going to go ahead and set up an A, B, C, and then we need to also do, so I'm going to go basically here, A. So we need to define several values. So we need delta FA equals, we need delta TA equals, we need TA equals, and we need F Nyquist A, and we need equals, we need F sub S A equals, and then we need big N A equals. I'm going to put capital A's here. So we need to figure out these values. And then I'm going to copy and paste this, and we're going to do it for the other ones. So first things first, do we see any mirroring here? Nope. So we know this delta F, what is it, 0.51, 1.5. So our delta F is already 0.5 hertz. Fantastic. We also know that if there's no mirroring, we know that this, which is 8.5, 8.5, 9, 9.5. So this is 9.5 right here. And so what we're going to do here, our F Nyquist is equal to 9.5. We know our F sub S should be twice that. So it should be 2 times 9.5. We know that our delta T is going to be equal to, actually I'm going to pull this over here because this will be helpful. Our delta T is just equal to 1 divided by F sub S A. Excellent. Our big N, we know we can solve that in multiple ways, but we can say, actually I'm going to start to do, and then our TA is equal to 1 divided by delta FA. So let's go ahead and let's start to look at these. That's our delta FA. Here, good. That's our F Nyquist. That's our F sub S. And then we know this is our delta T. And we know that our big N, we can solve it a number of ways. So again, we can also solve delta FA equals to 1 divided by big N A times delta T FA. Delta TA. So we can solve it that way. We can also know that, we can solve that f Nyquist A is equal to big N divided by 2 times delta f A. And we can also double check that the number of harmonics should be big N over 2. So basically, big N is that, 38 divided by 2. So we should have 19 harmonics. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and we got it. Fantastic. All right. What about the next problem? Let's go ahead and move into it. So let's go ahead and look at what we've got right here. So let's copy and paste this. And I'm just going to put this as B. But I'm just going to redefine some of these values. I know it's not good practice, but so in this problem, our delta F is now 1. So our delta F is 1. And actually, we can make the determination before we move on here. So if our F sub S is 19, we're not going to have any signal aliasing, so we're good. And our delta F is 0.5, we're also good. So A will work for this problem. Fantastic. All right. Now we have our period here. We have our delta F. Already we know we're going to get basically spectral leakage. There's no mirroring. There's periodicity, but there is no mirroring. And it looks like, so our F Nyquist is going to be 9. So 2 times F Nyquist here. Our delta F or our delta A we can solve. So now we're 19. We can also solve with F Nyquist here. Actually, hold on a second. So where's our F Nyquist is here. So 1 over, make sure here, our delta F, our delta, oh yeah, we need our delta TA. So be careful about that. So our delta TA is just 1 over FSA, which is right here. And so now when we rerun this, oops, we should be able to get this. Excuse me. There. Be careful. Again, that's why you take your time and actually just redefine all the variables and get through this. So it should be 18. We also know again. So if big N is 18, we should have 9 harmonics. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. Now, finally, we have this last problem. Now, this is a tricky one because we actually see a mirror here, right? So we're mirrored on kind of one side of one another. And it's a tricky mirror because we basically have to we kind of see the periodicity here, and then we see essentially that mirror through here, but there's not kind of like this middle value like we've seen on kind of other mirrors. And the reason is because we're actually, we're going to actually see how to deal with this one. But you're going to see one of the issues is, so picking essentially where the mirror continues here and where effectively it ends. So we see essentially a mirror that goes through here. We see the values matched, but this magnitude and this magnitude essentially is the same here. So what we're going to do is we're going to say, okay, there's a mirror. We know that in this problem, we'll go through up here. Let's go through here. All right. So our delta F, though, so 0.51, 1.52, so 0.5. We have our delta T. Now this is where it's going to get a little tricky. So if we select, so we have 4.5, and then we have 5 hertz here. If you think that the mirror ends here, it's not a bad value. So my F Nyquist would be 4.5. So then my F sub S would be 2 times 4.5, which is good. Here's our delta T. We can solve for this here, and we can find our value. And we can also say that our F Nyquist here is as such. And we can count 1, 2, 3, 4, 5, 6, 7, 8, 9. Makes sense, right? Because it's half of that value. There we go. So We know it's mirrored. We know that's our F Nyquist, and then we're mirrored on the other side. So will this work? Unfortunately not, because F sub s is not twice 7.5. So we need to be at least greater than 15 in order to get that value. So A will work though. So that's a cool finding. So we can see A has an F sub s greater than 15. Our delta F 0.5 is going to allow us to hit all those values. And then we're going to be able to plot, and we can actually see, right? Big N divided by 2 will give us, essentially, so 19 times delta F, or 0.5. We're going to be able to hit past our highest frequency here. And that's it. That is the problem 3. We'll see you in the next video. Thanks. Bye.